starting the recording, so I can say officially, Happy Garbage Day. It's a lovely Tuesday. It actually rained this morning. That was so exciting. My lawn looks terrible right now. It's like brown and dead, and so the rain was nice. Nice change of pace. Let's see here. Speaking of changes of pace, you have seen my announcements. We're meeting on Zoom only on Thursday. So pajamas at home for everyone. Let's see what else is going on. You have a homework assignment due tomorrow. There's one question that I've gotten a lot of questions about, and I wanted to bring up. I think it is question 59. Does that sound right? It's asking how we know whether or not a linear slope approximates the saturated means. So you can think of that. I have a slide actually that I'm going to do that was in lecture 3, but I'll pull it up for right now. So if you think of it from this perspective, parsimony to good fit, like the simplest model for the means you would have with respect to time is empty, just one fixed intercept. And the most complex version you would have is saturated means, in which basically each mean gets to be whatever it wants through an intercept in a series of slopes. So a linear slope is be one of these in-between options. So the question is, does the line fit the means? So it's a question that phrases itself in terms of not worse, right? Does the linear slope fit not worse relative to letting each mean be what it wants? And so that would be, what kind of test? I'll just give you the answer. What kind of test to see if something fits not worse? Yeah, likelihood ratio test. Now the question is, should it be the ML version or the REML version? Because it is only valid to compare different models for the means and fixed effects under one but not the other. So I'll let you ponder that one. But that one I realized we hadn't really talked about explicitly, and so I wanted to try and make that explicit. We're going to do more of that in class in the next few weeks. So any other homework questions that I can help you with at the moment? Due tomorrow night, Wednesday. Zoomers? I got the chat open if you want to type or talk. Okay, well, office hours tomorrow if there's any last minute questions as usual. Let's see, your next thing to do is formative assessment number 4. I opened that this morning, so that will be due next Monday. And I will let you know when homework 3 is available. It's going to depend on how much we get through this week. If we get through what I want to get through, then it can be due then. If we don't, then I'll have to push it back 2 days. So we'll see. Keep you in suspense. All right, let's see. Question?
Can I ask what's on formative assessment 4? Is it lecture 5 or lecture 6 or some of both?
It is, I gotta remind myself actually. Let's pull it up. We've hit the point in the semester where I cannot remember what I had for lunch, let alone what I did yesterday. Let's see. I know that Vladimir's going to go over it. I say, yeah, you noped out of that one. That's fine. It's optional. Preview. Okay, so this is lecture 5 for the first one, and it will be this week for the other 2. There's only 3 questions this time. So. Any other questions or things I'm forgetting? No, we're good? Then I was debating the order of operations here. I feel like we could use more review before diving into stuff. So the good news is that example 6A is like 3/4 review, and then the last 2 models or 3 models are new. So I think if we dive into that first, that might help. We can work through saturated means, empty models, random linear, that kind of stuff. Sound good? All right. Then example 6A. So just to warn you, I have 4 parts to example 6. There's A, B, C, and D, because they're different kinds of nonlinear. So the download files that are posted on the website, which I just, nope, did I close out of that? Nope. let me show you that link right here. So the example 6 files right here are going to go through all 4. That's why there's so many of them and they're so long. I'm still working on rebuilding the handouts for 6B and 6D. I've got 6C done because that one's only available in SAS as well. So this will be all the files that you need for the next several weeks. Okay, so this is an example based on the same data set from the second part of Chapter 3. And this is also what is featured in Chapter 6 of the book. So the examples follow pretty straightforwardly with Chapter 6. These are real data. I did not doctor them, I did not simulate them. So this is a case in which I honestly don't know what the right answer is in terms of what model would have generated these data, which makes it a good example. Because in real life, you're not going to know what the right answer is going to be. So in this example, we will build up through examining quadratic change. So polynomial trends is the title of this. Eventually, I've got code for an output for Stata and R. I'm alternating output between the two to try and eliminate redundancy when possible. And SAS stuff is online as usual. So in terms of data setup, there's a lot of code here that's not relevant yet. This is not relevant yet, so I'll skip that for now. But I'm importing a data format from Excel. I am generating in Stata here my time predictor variable by centering session, which is my indicator for time, as -1. That way the first session is going to be time 0. So the backstory to these data, they were collected over a 2-week period, 6 sessions. The outcome is response time to a speeded task. It's called number match 3, where there's 3 digits above a line on a screen and 3 digits below a line, and as quickly as possible, the person has to say whether it's the same 3 digits. So people should improve on this task, which means the response time should decrease as a function of practice. And it was 6 sessions over a 2-week period. We are only keeping track of which session a given observation is from, because it doesn't really matter if it was Tuesday or Wednesday. It only matters if this is the second time they've done the task or the third time or the fourth time. And the purpose is to examine reaction time practice effects independent of aging. So this is a sample of older adults, but by keeping the timing under a 2-week period, we can try to isolate out what would be age-related decline, which we're controlling for, versus practice effects. So this is the first occasion out of what is known as a measurement burst design, in which this 6th session protocol is repeated at 6-month intervals. That way they can look at change in optimal performance over time. But just the first 6 sessions. Chapter 10 has the full design with measurement burst, and as a 3-level model, by the way. So time 0 is session 1. And for reasons to be shown, I have to make the squared version in Stata. Turns out it won't let me have what it calls a factor variable in the random section, which would be designated with a hashtag to create the interaction term on the fly, so I made it myself. And as the good data analyst I learned to be, I'm adding labels for future self. R doesn't use labels. It's one of the things that I've gotten no way of. As I said, we'll skip this for right here. And then I made one global variable for the last occasion that I'm using in a couple of places. R, folks, I'm not going to forget about you. So setting the working directory as usual. Example 6, sheet specifically. By the way, on the web page, I forgot to mention this earlier, next to the due date for this homework that's due tomorrow, I put up a new handout called Steps to Doing Homework. I had created that for my other class, but in case you're not used to doing homework for this class that involves data analysis, that should help you, just a sort of a step-by-step what you should do first and what materials you'll need to download. So that made me think of that for some reason. I am making sure it's a data frame as needed. I don't know what it imports as, that's just something I do sort of superstitiously, and sorting by person and ID. Making my time variable here, skipping this code for now, and I'm saving 2 objects, the number of occasions and also the total number of observations, and those will show up in a couple of formulas as well. So first step then, get the answer key. So because we have the same 6 possible occasions, time is balanced. That means we know what the right answer is with respect to the patterns of means and the variances and covariances that this model is trying to reproduce. So we're starting with what I call the answer key model, model 0 as it is labeled, saturated means, unstructured variances. So you've seen this one before, and this was actually the last model in example 3B as well. So the model for the means, the fixed effects, looks like this right here. RT hat, meaning the part that is predicted by just the fixed effects, has an intercept, as well as 5 binary predictors for each subsequent session after 1. And the unstructured part of it cannot be easily shown in a scalar equation like this, so we just have a label here that that's what it's going to be. So I.session in Stata, I'm using GLS in R, and I'm treating session as a factor. So what that is doing then is treating time as a categorical predictor, as a grouping variable, thus implementing this model for the means right here. So it's doing the dummy coding for you, essentially. I don't have a random intercept, so that's why I have the no constant here. I don't have anything in the code for GLS that would indicate a random intercept. I don't have to turn that off the way I do in Stata. I do have residuals unstructured, so that's the part that's going to give me all possible variances and covariances only in the R matrix. And the code down here does that similarly within the GLS framework. And the first set of output here then, R matrix and R core, asking for in Stata. I'm going to ask for those in R as well. The contrast here gives me the omnibus F-test that we'll see down below. And then margins gives me the predicted outcome per occasion, which I'm then going to throw in a plot and then get mean differences as well. So you've seen most of this before. And then R folks, here's the output here. We've got -2 log likelihood that I requested. And then here's the model for the means. So note there's 6 fixed effects in total, 1 intercept and 5 slopes. I've got them labeled for you. Because of the default, the first occasion is going to be for time 0, session 1. And then these describe the changes relative to that. So 146 is how much lower session 2 is than 1. -211 is how much lower 3 is than 1. So these are all referencing back to a reference occasion number 1. So here's the pattern. So within GLS, they have a function that readily prints the R matrix. So this is getVarCov. 101 is the first case in my data set according to person ID. So that's something you would need to change to match yours. Type equals marginal. That means put it all back together again. So if we were using a model that had both G at level 2 and R at level 1, this would give me V back together again. But because this model has no random effects yet, it only has an unstructured R matrix, R and V are the same thing. So this is the answer key with respect to the model for the variance. This is what the random effects are trying to reproduce, this pattern. So if we look at this, just eyeball it for a second. What's on the diagonal here? We'll throw some softball questions at you. What are these numbers? Variances. Do they look the same or different? I've got, these are very large numbers because this is response time in milliseconds, by the way. I've got like 300,000 and some odd, 259,000, 233,000, and so on. Same or different? Yeah, they're still very large. It looks like they're getting smaller. Yeah, it looks like people are becoming more homogeneous over time. That is a dead giveaway that we have individual differences in change. Yes, 2 Zoomers voting for different, I agree. Covariances are going to differ over time because the variances do. So it's easier than to judge that by staring at a correlation matrix. So these are the pairwise correlations across occasions. They're all pretty high, but they do have some variability. So for instance, 0.8, 0.76, all the way up to 0.93, I think is the highest one that I've seen in here. So again, this pattern is what the random effects are for. That's their job, is to reproduce these patterns right here. This is my F-test. What is it telling me? There. Now it's aligned. What's my F-test telling me? You'll note that I've labeled this less than usual because we're going to do more of this Q&A thing. That something is significant, but by now we know better than to just look at p-values. Well, that is probably true. But yes, something is significant.
There's an overall difference between occasions?
there's an overall difference between what?
Occasions or sessions.
Yes, occasions or sessions, yeah. So these means down here are different. So this is a joint test of the 5 slopes that work together to create the 6 means. So the differences are not 0 is what this is telling us. So there is some kind of difference in the means over time. So it's the joint test of all 5 of these slopes. That's what that F is for. It's provided for you. If you use GLS using joint tests, it's provided using ANOVA if you use Elmer instead. So here are the means. Do they look the same or different? Different. Yeah, we just learned that. Different in a pattern or different like randomly? I see sort of a pattern. They're going down, right? As you would expect. Question from the Zoomers. So if it wasn't significant, is that game over in terms of longitudinal analysis? Oh, great question. What do you think? If this p-value were not significant, would it be game over, take my ball and go home? No? No? A couple shaking their head. Well, so that would mean there's no change on average, right? Have I learned anything about individual differences in change? Not from the F-test. So the answer, no. It does not mean game over. There's still a lot of things that can be done in the absence of overall change. There are a lot of studies that are focused on variability rather than change. So like, how sad are you today? You know, how much social support do you feel today? These are things that fluctuate. They don't necessarily go up or down in a pattern. Here is, in the margins here, how the model is recreating each of these means. So it is an intercept plus each of the slopes as a linear combination. That is what this EM means command is providing. I also asked for all pairwise differences, and I did not bother with type 1 error control. You can do that if you feel like it. And so then those pairwise differences are created as these linear combinations as well. So 2 questions then at the bottom here for you. By what other name do you know this total answer key model when it is estimated using least squares? So this is a crossover event for your other classes.
ANOVA?
One more word in front of it. I heard ANOVA.
ANOVA, yeah.
One more letter in front of it. I heard it. Zoomers? MANOVA. Yeah, this is MANOVA. This is a multivariate analysis of variance model because time is treated as a grouping variable. And we have an unstructured matrix, which is the same thing as what you would have the MANOVA approach to repeated measures. Same question, different class crossover. What is this model called when structural equation modeling land? I think about half of you were in this class before. The rest of you can stare at me. What is this called in SEM class? When we have all the means be what they want, all the variances be what they want, and all the covariances be what they want. Nothing? All right, I'll give you a hint. It is not the hoe. There's a story. She's like, what?
Yeah, come back for that one.
There's a story, I promise. No?
H1?
H1, yes. This is the saturated model. This is the answer key in SEM against which we judge the absolute fit of any factor model. It's called H1 in your output. The alternative is labeled as HO in your output, which means your model. And a student once asked me in office hours which was which, and she's like, am I the hoe? And I was like, what? And then I realized what she was asking, like, is your model the HO model? Yes, you are the hoe. And so after that, I never forgot which was which. So H1 is this one. And so that means that it is indeed possible to test absolute fit if it is possible to estimate this model, meaning we have enough people to pull off all the different parameters, and we have balanced time, where everyone is sharing the same schedule. Think of it in an SEM path model as 6 boxes in the model. for the 6 outcomes. That's the tie. Items or occasions in this context. And I made a picture. I made 2 pictures, in fact. Here's the trends. So the picture on the left, this is the means over time. So it looks like response time is improving. People are getting faster. That's what this downward trajectory means. Now, does it look like they're getting faster linearly or non-linearly? Yeah, kind of bendy, right? The extent to which they are improving appears to kind of slow down after about session 2. So a big improvement at first and then less improvement later on. Over here are the variances. They actually have the same type of pattern. They are declining over time. People are getting more homogeneous. And a spaghetti plot, by the way, of these data is in slide 2. So those trends don't necessarily cover everybody. There are some people who actually got worse before they got better. Probably they hated the task and weren't trying very hard, would be my hypothesis, because it's not meant to be a difficult task. So with respect to building our model, the picture on the left, the change in the means over time, that's what the fixed effects are for. Okay, fixed slopes related to time. We'll see several different varieties that could model this pattern of nonlinear change. On the right, the change in the variance over time and also the change in the covariance, not pictured, that's what the random effects are for. So I'm going to approach this from those 2 different sides of the model. Model for the means, fixed effects, describe average change. Model for the variance, random effects and residuals, describe variances and covariances. They each have their own job to do. Okay, how are we doing so far? Any questions or things you want to hear differently? All right, moving along then. So now we're starting from the opposite perspective and building up. So I'm essentially getting the 2 endpoints on the continuum. Worst possible model, best possible model. We just saw best, now this is worst. Nowhere to go but from here but up. So empty means random intercept. When you read about this model in the literature, you may also hear just empty model or unconditional means model are the 2 terms that I've seen for this alternatively. I've got the equations from the textbook here. So let's see. How many parameters are in this model? We got 1 vote for 2, 1 vote for, I heard 2 or 3. Another vote for 3. Let's take it side by side. How many fixed effects do we have? 1. Where is it? Intercept. Which one is it? The gamma looking thing. Yeah, gamma 0, 0. That's my fixed intercept. That's 1. So the model for the means has 1 parameter. How many parameters in the model for the variance then? It's 2. I've got a variance of the e's across occasions and people, and a variance of the u zeros, that's a random intercept, across people. So note the subscripts. I, because u is a person thing, its variance lives where?
No, in the diagonals.
In the diagonals of v, but it lives in G. Yep, G and R put back together again is what we're here. So level 2, variance of the random intercepts lives in the G matrix. These are person mean differences. Some people are faster at this period. That's what we're capturing. E then is, why are you off your line today? The line that we've drawn is a straight line that is parallel for everybody. So E variance across occasions and persons, assuming that it is the same over time and persons. Where does the E variance live? R matrix. G and R put back together again, make V for victory, or broken V. Take your pick. So then, I think you've seen most of the code for this before. I've got state output this time. What does that number tell me? 1770. Your outcome is response time in milliseconds. Mean response time? Yep. More specifically, I would say the mean of the person means in this data set is balanced and complete, so it would be the same number regardless, but in future data sets that may not be the case. So this is the mean of the person means. On average, it takes 1.770 seconds to do this task. Pretty fast. What's this number? 200,883. It's obvious to the people who made Stata output. It is not obvious to the rest of us. Well, there's only 3 parameters, right? There's one. Here's the other 2. Which one is this? It's in the person section of the table. Yeah, that's the U0 variance. The variance of the U0s across people. Yep. So that's a point I'm trying to emphasize. This in the equation, that's one value. This is the U for person I. The variance across the U's for across all the I's is this number right here. That means this has to be what? Yeah, this one's a little better labeled, the variance of the residuals, level 1 E's across occasions and people. This is my likelihood ratio test as to whether that random intercept variance is significant. A chi-square of about 700, yeah, we'll call it significant. Next stop, intra-class correlation. What's that number tell me?
$82% is between person variance.
82% is between persons. 82% is cross-sectional variation due to mean differences. 82% is about what we would expect if we did the study once. Like these are differences between people. So only 18% of the variability has to do with some kind of change over time or fluctuation over time. Also, 0.82 is the average correlation across occasions from the same person. You can also think of it that way. So relative to the next model, I need to save this number right here because I'm going to want to calculate an R-square value for it, a pseudo R-square value for it. So that's what the rest of this code is doing. I saved the results of this model to a matrix called empty RI. I'm now asking it to be printed so I can see the contents. So the first column, this is all stuff for the fixed intercept. The second column is stuff for the random intercept variance, and the last column is stuff for the residual variance. But this number right here does not match this number. This is the log of the standard deviation of that variance, because that's what's being estimated directly in Stata. So to turn it back into a variance, I had to square and exponentiate it. So I saved the result to a new programming variable, kind of like an object in R or a macro variable in SAS, called empty resvar, meaning residual variance from the empty model. And then I had it printed just to make sure that I got it right, and indeed it is. So I'm saving that to do math on. And the R code that I wrote does the same thing. I don't have to isolate it because everything is saved in this object. When you name the results of an analysis, it stores everything for you in one fell swoop. The only question then is trying to find the things you want out of that object, which can be very tricky sometimes. I am adding something to my Elmer call here for these examples that you have not seen yet. It's this option right here for control. There are different approaches to optimization that are used in Elmer. I believe there's 3 or 4. And through trial and error, I have found this one matches SAS and Stata's results the closest. So I'm throwing that in here, even if it's not strictly necessary in some of these simpler models, because I do know that it gets to the point during quadratic models that it is necessary. So, yes?
Can I ask why were you using Elmer for the empty means random intercept model? I mean, and also why GLS for the saturated one? Because
Yes.
I remember Elmer can only handle like diagonal variants in the R matrix.
That is correct.
We can do it for this one, and we couldn't do it for unstructured. But is there a reason why we like Elmer better and would rather do Elmer if we have the option to do it?
Yes. So let me make sure the question was audible to the Zoomers and the recording. I started out with the saturated means unstructured variance model, and the unstructured part is the key here, using GLS, which is from the NLME package. Now this has a lot more flexibility in terms of R matrices and allows you to add random effects if you switch to the LME function, but I have found that it is not good at getting the degrees of freedom right. It has issues with Satterthwaite degrees of freedom in most of the models that I've tried. So for that reason, I prefer Elmer over LME when it's possible to do the same model in both. But towards the end of the example, when I ask questions like, should there be a residual correlation in the R matrix, then I have to switch back to LME to be able to answer that question. In which case, then my fixed effects may not have the right denominator degrees of freedom.
Thank you.
Sure. So yes, I'm in Elmer. I changed the estimation preference as a default. I'm going to keep that throughout the whole example so that then hopefully you'll have less discrepancy across your homework values. And it is RUNOVA to do likelihood ratio tests if you're using Elmer, not an. Yeah. That is saying basically for every random effect variance in your model, it's going to estimate a nested model without it and then give you a test of fit against it. So if I had 3 random effects, there'd be 3 lines, each like taking one out at a time. So I believe this is a default, but I like to put the defaults in here to make things explicit when possible. That way you don't necessarily have to fit the comparison model to answer the question about whether your random effect is significant. Now I usually do that though because it's useful to see the contribution of just that. So for instance, the next model that I'm fitting is fixed linear time random intercept. In other longitudinal textbooks, they would go straight to random linear and do a likelihood ratio test to see whether it helped. Now there's 2 issues with that. Can I do that in REML? Can I compare empty means random intercept up to random linear, where I would add a linear slope on the fixed side and the random side at the same time? Nope, can't do that likelihood test in REML. I would have to switch to ML, which would give me downwardly biased variance components in smaller level 2 samples. The other reason that is dissatisfying to me is, let's say your result is significant. Was it the fixed slope that helped, or the random slope, or both? I think those are important distinctions. So that's the reason why I proceed sort of in a stepwise pattern, even though technically speaking, we don't necessarily have to. So I have now switched to fixed linear time. What's new in my equation? What's new? Thought I heard it.
Gamma 1, 0.
Gamma 1, 0. This guy right here. So this is how each person is going to get their own linear slope, and that is defined in the level 1 model right here. So an individual slope as a second level 2 outcome is designed with just a fixed effect right now. So everybody gets the same. And I saw your question, Vladimir. Did I answer that sufficiently? I was talking about Elmer control just a second ago.
Yeah, sorry, yes.
Okay, yes.
But
It's not necessary in all the models, but because I just have the same code and I'm only changing the model part, I just left it in.
got it, thank you.
Yep, yep. So yes, 1 new parameter. And this is adding a fixed effect, which means we can stare conveniently at the p-value for it. We don't need to do a likelihood ratio test, and we couldn't anyway because this is REML and not ML. All right then, so we've got stata output, or excuse me, no stata output, R output this time. So you've seen all of this before, c dot time being treated as a slope now. So time is no longer a discrete variable, it is a continuous variable, quantitative variable, meaning we're giving it a linear slope. saving the results of this model, asking for predicted outcomes at each occasion from the linear model so we can see how well that looks like it fits. This set of 6 lincoms is done by margins, so that one line does everything above it. Sometimes it's easier to write it out if you have a very complex function, but this will do it in this case. I am now saving the residual variance out of this new model, making it into a variance, and then using it to compute a pseudo R-square. So this is the proportion reduction in residual variance. We'll see that in the R output down below. And in Elmer, then, here's time as my new fixed effect. Everything else should be pretty much the same. In Elmer, it prints deviance as your -2 log likelihood value. My random intercept variance has actually increased because I have explained a whole lot of my residual variance. So now, what does my intercept tell me? It is about 1900.
Times 0.
Time 0 predicted mean. So it's not the actual mean at time 0, which is what the saturated means would give you. This is where the line says the mean would be. It's the predicted intercept. And this model says what happens from there. The first occasion has a predicted mean of about 1900 milliseconds. After that, what happens?
On average, it gets worse by -51 milliseconds. Each occasion.
Response time does go down by 51 and some change milliseconds per occasion. So this is a slope per unit time, per session of practice is the way I would say it. But I would not say gets worse, because this is response time, and faster is better. They're improving. Yeah.
It's the golf homework.
I know. Yes, I have a homework that involving golf scores that trips people up because golf is a sport in which the lower score is better. And every time someone complains about that, I'm like, there are lots of outcomes that we want to see go down, right? Like diseases and crime and poverty, like air pollution, flooding. There's lots of things that we want to try and reduce over time, and the reduction would be a good thing. Debt. Violence, illness. Yeah, Alex is having flashbacks about the golf homework. Yeah, the intermediate kids just finished that one, so. Yeah, they hate me right now too. But theirs didn't have any interaction terms though. I was nice to them. Yeah, no, the generalized group got the full model. Yep. Sorry, not sorry. Let's see here. I have asked for all the predicted means at each occasion. So I have my blue one here. This is a formatting find and replace fail. There we go. Let's fix that. Contest 1D is how you ask for linear combinations of fixed effects as single parameters. The 1D, I think, stands for one dimension. The analog to ask for multiple fixed slopes, a joint test, is MD. So the GLHT package I normally use for this does not work with Elmer, to the best of my knowledge. So I had to find this one. It's within the Elmer test package. So what is happening then is that I'm saying I'd like one fixed intercept, please, at each of these occasions, because that will be the base point for starting my prediction. And then I'm filling in the value of time for which I want the prediction. And time starts at 0, so it's ranging from 0 to 5. Over the weekend, Jonathan wrote a little function for me and showed me how to write little functions, and now I'm writing functions left and right in R. So I made a little function that spits out the means, and it's in your download folder. So I made a little function for polynomial models that will work for that. So there's 2 or 3 other functions you'll see in these handouts over the next couple of weeks as well. This is one that Jonathan wrote, though. As you might imagine, his function is called the pseudo R-squaredinator. And his function is much better than my function. It has like traps and like things to make sure that everything is like you're doing the right thing. I'm just trusting you to do the right thing. So the two arguments that it takes, what is the smaller model and what is the larger model that you want to compare? So in this case, we are saying relative to the empty model, how much variance has been explained in the model with fixed linear time? And it's printing out the R-square for both terms because it does that. It only works for two-level nested models, by the way. So this one down here is for the the residual variance at level 1. So we just explained about 21% of the E variance by allowing fixed linear time to have a slope. Why are you off your line? Oh, because the line was flat, and now you need a line that's not flat. So the E variance is reduced. And because this is a fixed effect, I would call it a reduction. We have explained some of the E variance by adding fixed linear time. Because the residual variance went down at level 1, the random intercept variance went up at level 2. So a negative pseudo R-square means an increase in variance, but it's just because of how it's estimated. It's not actually a problem. Okay. How are we doing so far? One more? Random linear time. How many new terms have I added to the model? Which one is new? Yeah, U1, right here. That's brand new. What is that thing?
The deviance of each person from the linear time slope.
Yep, U1 is how far off each person's slope is from the average slope, which is given by gamma 1O. So U1 then is a random slope. A random linear time slope, to be specific.
But we have 6 parameters in this model.
We do. I was just going to say that because I added something else, but it's not in the equation.
Because the two U's relate.
Yep, I have added a covariance or a correlation between U0 and U1 in the G matrix because they come from the same person. So U's from the same person should be related. R does that by default. Stata does that if you add a command with which to do so. So yes, not shown in the scalar equations is the covariance between these two. They would show up in the matrix equations. Where does it show up in the code? We'll look at Stata first and then R. I didn't turn it yellow this time. Made it a scavenger hunt instead. Where does it show up, Stata users? I'm looking at the HESA side over here. And the sociology folks. Where's my random time slope show up? After person ID. Thank you. There it is. Yes. Note it does not have a C dot. The covariance part also shows up here. So covariance unstructured refers to your G matrix. And unstructured is the only kind that makes sense in the vast majority of cases. Because you want the U variances to be whatever they want, you want their covariance to be whatever they want. So storing results from the model here. Let me get to the R code since I'm finding the stuff. In the R code, where does my random slope show up? Yeah, here it is, in the parentheses. So note it's in 2 different places because it's doing 2 different things. Outside the parenthesis, this is the fixed slope on average. Inside the parenthesis is specific to person ID as a random slope. Yep. Yes, indeed. All right, let's see what happens. So the fixed effects are exactly the same, not surprising because we added to the random side of the model. The interpretation of the fixed linear time slope, though, has changed. It's now the average of the person slopes rather than just the mean for the entire column. The 2 new parameters that we've added in the model for the variance are the first 2 lines under the random effects parameters. Var time excuse me, nope, I take that back. The first one and the third one. It puts them in a weird order. So var_time is my slope variance, var_cons is my intercept variance, and then this is a covariance between the two. Stata also prints 95% confidence intervals. This one doesn't overlap 0. That's a good sign, right? If I want to have slope variance at least. Is this a hypothesis test though? Nope, not really. What do I want to do to decide whether or not I like having my random slope variance in the model and this covariance that goes with it? -2 log likelihood ratio test. Can I use this one? Nope. The 3, that's the problem. What this is testing is if you need any random effect variances and covariances, anything in the G matrix at all. That's what this test is doing. It's comparing it to a standard linear regression with the same fixed effects. SStat recovariance, relevel, person ID correlation. That's the G-core matrix. That is the correlation between the intercept and the slope. So it's a negative relationship between how fast you are at time 0 and how much you improve. So people who start out higher change more. Which stands to reason, right? If you're really slow at this, you have a lot of room to improve. I asked for the V matrix. That's another SStat command, and it printed it in scientific notation, which is useless. I spent 15 minutes trying to solve that problem and decided I would just print it in R instead. So if anyone knows how to fix that, please let me know. Here's the correlation, though, for V-core. So this is the pattern that the random linear time slope variance has created. It's changing correlations over time because each of these is now a specific function of which occasion it is, and the random linear slope variance and covariance. Next up is my likelihood ratio test. So I asked it to compare the fit of the random linear model as the larger one, and then the nested model, the smaller one, is listed second. That's my fixed linear one. Survey says test value of 43 tells me what? Like your results section would say random slope variance was significant, blah, 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 comma, indicating that improvement, the model improved, which means because Zoomers can play too. What's the practical interpretation? Because that's what I'm looking for. Like, what have we learned about the data?
We need the added term.
We need the added term. We need the random slope. We've replicated the data variance better. Yes, all of those things are true. How do I explain it to my mom?
People differ in their amount, their rate of change.
People differ in their linear rate of change. Yes, that's how you explain it to mom. I wouldn't say linear rate of change, but some people get more better faster. How's that? Something like that. Yes, there are individual differences in linear change. That's what we've learned. And we've learned that because the model fit better, because it means we've replicated the data better on the variances and covariances side. The data got taller is another way you add to that in terms of the multivariate normal distribution as the formula for height in maximizing the model's likelihood. I then did some stuff to get additional values. So I saved the residual variance out of this model for comparison by the next one. I found it in the last spot. So it looks like the residual variance is always the last column. The order of these are, I believe, in the same order as given in this output. It's hard to tell, though, by looking at it. All right, in R then, so we've got time in the two places. Here's the V matrix. So this is the pattern of variance and covariance over time that a random linear model predicts. Here's the formula by which it predicts it. So the numbers on the diagonal, the variances, they start out with the random intercept variance, and they end with the residual variance. So like the outside is the compound symmetries part that the random intercept had. It's the inside that's new. So it's a function of what occasion it is squared times the random linear slope variance plus 2 times whatever occasion it is times the covariance. So this time squared thing in here, what that's going to do is create a pattern of variance that's a parabola, a U, like this. So a random linear model implies that the variance changes quadratically over time squared. There is an occasion at which it will be at the minimum, and then it will increase on either side of it. Covariances, same idea. They start off with the random intercept variance. That's what we had in the compound symmetry model, and then it adds to it functions of the random slope variance and covariance that have to do with which occasions are being correlated or covaried. So this is the machinery that created this V matrix. And I made a function. See, look. I'm so proud of myself. I have a little function that's called print V. Do you know what it does? It prints V. It makes it and then it prints it. And it worked for all the models, and I'm so happy. I know. I didn't write the inside of the function. I stole it from some guy's Stack Exchange website, but I wrote the wrapper to print it. So, very proud of myself.
How does this change your R?
Oh,
Your thoughts on R, if at all?
does this change my thoughts on R? No, I still hate it. But now I have gotten to at least some level of functionality of like I'm getting closer to what I can do in other programs. Like I know how to do some programming in SPSS. I know how to do a lot in SAS. I'm learning a little bit of Stata here and there to do the same thing. I haven't conquered functions in Stata yet, though. That'll be the last hurrah. But all right, then we've caught up in terms of everything that you know how to do. Do you want to see what's coming? Yeah. So let me jump back in here. Going back to the slides then to introduce the world of quadratics. So our task then is figuring out what kind of change on average occurs over time with respect to the fixed effects. So this is presupposing we know what the metric of time is. I'm going to leave this here as a placeholder. It's not always obvious. This is going to be one of the first topics in the advanced class, by the way, is what happens if people differ in time when they enter your study, because the model needs to adapt for that. Also then thinking about what kind of theoretical process generated the observed trajectories, like what would make sense in terms of the construct and how it's changing. For something like a practice effect, I would expect some kind of curve that sort of eventually levels off, like you stop benefiting from practice at some point. So a quadratic model actually doesn't coincide with that very well. I'll show you an alternative that does, called exponential. Is it continuous or discontinuous? Are there things that happen that would abruptly change the trajectory, like an intervention, or, I don't know, COVID, or a hurricane, or something? So the choices that we have then are more complex than an empty model, hopefully less complex than saturated means. And we can do the in-between options even if we don't have balance time, because it's a function. So here is a plot of response time for this example in the black line. So this is what we're trying to approximate. The red line right here is what the empty model says. So these are the two benchmarks. The red line is the worst, the black line is the best. Now, if I drew a straight line through this, how well do you think it's going to fit? Like we just did in our example. Better than empty, but this does not look straight. So fitting a line through this is probably going to under-predict the first occasion and over-predict the last. So we need something bendy besides linear. The same idea on the model for the variance side. So from a substantive perspective, what we're interested in is examining what kind of individual differences we have. Is it enough to give people their own intercept, or we need to give them their own slope? If we have multiple slopes because we're describing nonlinear change, are there individual differences in both of them? That's an empirical question. So for the intercept, because the intercept is going to become conditional on time 0, once you have a random time slope, you want to think about where to put it. So individual differences in the outcome level. That can be at the beginning, it could be in the middle, it could be in the end. It's up to you. But those are going to be different numbers. So in our example, for example, the random intercept variance went from, let me go back to the fixed linear model for a second here, 202, 423. After adding the random linear term, it went up to 253. So it's very different because it's not the same thing.
Because it's now 0, and we saw the variance got lower over time, so it's the worst at time 0.
Exactly right. So in this picture, like people are more spread out at the first occasion relative to the last occasion. We saw that the variances are declining over time. And so by putting in a random time slope, you have made your random intercept conditional on time 0. In the same way that putting in a fixed time slope makes your fixed intercept conditional on time 0. It's the same thing, but it's on two different sides of the model.
If the variance was getting worse over time, we would see the other way around when we go from the empty means to the random intercept model.
Yes, so if this were a case where people were like the same at the start and then they grew apart, then if the start were time 0, you'd see a tiny variance there, and potentially a non-estimable one, depending on how small it is, in which case I would move the intercept off of it, so it's easier to estimate. Yep. Yes, so it matters where time 0 is once you have random slopes in the model because the intercept is conditional on time 0. So that is something to think about. It will be a different number at each potential occasion. And then individual differences in the magnitude of change if you have enough data to pull that off. So this is what we care about from like a theoretical research perspective. What is happening behind the scenes, though, is this idea of matching patterns. The variances and covariances across occasions can be better approximated once we have random slopes of time-related predictors in the model. A compound symmetry model, a random intercept only model, is consistent with parallel change, parallel trajectories. So we're back to this picture again, with now just random effects models being the thing that's in the middle. We're trying to get something that is not worse than unstructured. And unstructured is only possible if we have balanced data. So here's the equivalent picture for the variance side. The black line is what the variances were estimated to be at each occasion. The dotted blue line is the prediction from a random intercept only model, constant variance over time. So this to me looks like the left half of the U that the random linear model is going to predict. All right, so wrapping up the big picture. Model for the means, your fixed effects. They are trying to describe change on average. Model for the variance, your random effect variances and covariances, residual variances and any covariance of those are trying to approximate the patterns of variance and covariance in your data. They're also trying to give a quantification of individual differences in intercept and in change. All right, this I'm going to skip for a second and come back to it. So this is something that is not in the book. It's a bonus. Something I figured out after I published the book. How to test absolute fit when using REML estimation instead of ML. So polynomials then. If you take time and square it, that's what we're talking about. So mean change over time can be described with polynomial fixed effects. Linear is what we have so far. Quadratic is time squared. That implies that the linear slope changes. In physics terms, that's known as acceleration or deceleration, whereas linear is known as velocity. And in cubics, time to the third power. That is known, I had to look this up. It's a jerk, a surge, or a jolt. You heard these terms before? You have?
Well, I majored in physics. So.
Okay, so can I get a judge's ruling? People use these terms? So people actually say this is a jerk?
I do have to.
Because that's what I thought. I'm like, well, you're a jerk if you make me do a cubic model.
I do have have to lodge a complaint about acceleration, we just call it acceleration.
No,
Even
no,
if you're decreasing acceleration.
fair. Okay, I can live with that. It's shorter if you just say it one way. That's for sure. You can keep going, so you can have time to the fourth power as a quartic, quintic, sextic, septic. I think once we get to septic, that sounds pretty bad. I think that's a stopping point. The rules generally, though, you can have fixed time slopes up to the number of occasions minus 1. So if you wanted to have a cubic trend, that means you need 4 occasions. If you wanted to have a quartic trend, you'd need 5 occasions. At that point, though, it would be the same thing as a saturated means model. So like if I have 3 occasions, I can estimate 3 means, or I can have an intercept, a linear slope, and a quadratic slope, 3 parameters, same. So it's n minus 1 because we already have a fixed intercept, that's why. And I have seen a cubic work before, but I've never seen anything past it that actually made any sense. A cubic would be, like, there was one study that I helped with where it was a growth pattern that was sort of linear, and then it slowed down, and then all of a sudden it took off again. So there's a change in the change of the change in a cubic model. The rule is to talk about what the quadratic term does to your linear change function, you need to multiply it by 2. And I can give you 3 reasons for that. The first is because it's a derivative. So if you take the derivative of a function with respect to x, which is time here, that would mean that the first derivative, the 50 would go away, 4 would come down, and then the exponent that's on the x comes down in front of it. So we're talking about computing the second derivative, which is half the quadratic, so you have to multiply it by 2. If you're like, yeah, I don't do derivatives, what else you got? Interaction terms. Another way that you can think about this is following the rules of main effects and interactions. So in a typical linear model like regression, I might have one predictor x, one predictor z, and I can have their interaction term. And that would mean that the interaction is doing 2 things at the same time. You can talk about it as how z is moderating the effect of x, or you can talk about it as how x is moderating the effect of z. Both of those are equally correct. But if you put it in this context, time squared is an interaction as time by time. But there's no corresponding z second effect here. So it has to do its thing twice. Does that make sense? I think so. And the third reason is the mom reason, because I said so. I don't know why, just do it that way, just because I said so. So we're going to multiply the quadratic slope by 2 to talk about how it plays a role in the model. Here's some pictures. So in each of these pictures, time is centered so that 0 is the first occasion on the x-axis. And each of these pictures has a slope of 4 for the linear slope and a slope of 0.3 for the quadratic. They differ in sign. So if I start with the top left here, at time 0 specifically, the linear slope is 4. That is the slope of the line that is supposed to be tangent to this curve to the best of my PowerPoint drawing ability. So the same thing in terms of main effects and interactions applies here. When you have an interaction in the model, the corresponding main effect is conditional on the thing it interacts with being 0. Same thing here. The thing it interacts with being 0 is time. So this is the instantaneous linear slope specifically when time is 0. That's what a linear slope means in this context. Because it's going to change. So for every unit increase in time, this quadratic slope of positive 0.3 is going to make this more positive. And it's more positive by twice the quadratic slope per unit time. So the slope increases to 4.6 by time 1, 5.2 by time 2, and so forth. So I would call this accelerating growth or accelerating change. It's positive. Something like the growth of bacteria on your kitchen sponge over time, maybe, something that's heading up. COVID rates initially, much steeper than this, very close to a vertical asymptote. If we have the same positive linear slope of 4 at time 0, but now we pair it with a negative quadratic instead, now we have change that is slowing down. So I would say that the linear slope at time 0 of 4 is less positive by 0.6 per occasion further. So decelerating growth. Can I say decelerating, please?
Yeah, you can say.
Because I don't, is it, like accelerating means up,
Yeah.
like something is speeding
What
up.
would be negative acceleration?
Negative acceleration, okay. So this is either decelerating growth or negatively accelerating growth. Take your pick. Point of the story, when the signs are in opposite direction, the function is slowing down. The same thing happens from the opposite perspective in the bottom left picture. Now this is a negative linear slope paired with a positive quadratic. I would say this negative trend is becoming less negative by 0.6 per occasion. So there's decline, but the rate of decline is declining. And then you can have decline that is accelerating. In the cognitive aging literature, there are trends that we call terminal decline. When people start having health problems, everything sort of falls apart very quickly at once, sadly enough. So this would be like a terminal decline curve. Question, so decelerating growth would be something like a kid's height because it stops at some point despite being really fast initially. Yes, that is a great example. Changes in height and weight in infants, like they can double their weight within like a month or something. And fortunately, that's a little harder to do when you get older. Although I'm here to tell you, there is a change in your 40s for your metabolism. It's coming, okay? The change is real. Everything starts to fall apart in your 40s. Not that I would know, you know, because I'm going to be 35 forever.
I think it started for me at 25. Everything started.
It started at 25. I'm saying that there is a change point coming. Like there's an inflection point to the curve that's happening. All right, so then the rules about how to interpret things are the same as what you learned in terms of interaction terms, and if you haven't seen that in a while, here it is. So if I start with a model that has, on the fixed side, is what we're talking about, that has only a fixed intercept, that's the grand mean, because it's not conditional on anything. Once I add a fixed linear time slope, the fixed intercept is now specific to when time 0 is, but if the fixed linear time slope is the highest order term, then it's not conditional. So a linear slope is just, that's the slope, period. Once we add the fixed quadratic, then the fixed intercept is still conditional on time 0, so it hasn't changed interpretation, but it does change what its value would be, because now it's predicted at time 0 from a different function. It's a bendy line rather than a straight line. But time as a fixed slope, the fixed linear time slope, is now specific to time 0, and it will change as a function of where you've centered. Quadratic time is half the rate of acceleration, so you have to multiply it by 2, and it is unconditional because it's the highest order term. Can you imagine what would happen if I added a cubic, though?
Okay.
Then what? Would the fixed intercept change its interpretation if I added a cubic? No, it's still at time 0, it's just now it's a different prediction because it's a different shape. Would linear change? Different value because it's a different shape, but it's still conditional on time 0. What would happen to quadratic if I had a cubic term? Then it's at time 0 also. So all the lower order stuff is conditional on time 0. The highest order is not. Okay. You want to see it? Fixed quadratic model. Beta 2. Time squared. Because I have a third beta, I now have a third level 2 outcome. And its fixed effect is gamma 2O. 2 because it goes with beta 2. 0 because it's the starting point of how we build beta 2. Ta-da! I have a helper here to remind us how to predict what the intercept would be at each occasion. So that's my predicted outcome, is this function. The instantaneous linear slope at any occasion is the linear slope plus twice the quadratic times whichever time occasion you want the slope for. In Stata, I can make a quadratic slope on the fly using a hashtag. In R, I can do the same thing using whatever this thing is called. An I function, indicator function. Inhibit, Vladimir says. What am I inhibiting? My sanity? This is how you square things. It yelled at me when I tried to make an interaction term out of time by time, so I found this. So there we go. How about we see what happens next time? We down with that? Come back Thursday for the exciting conclusion of Is Our Line Bendy? As the world turns. All right, any questions as we wrap things up for today then?
So is there a limitation for the number of occasions that we measure with quadratic column?
You need at least 3 to fit a fixed quadratic. And that would give you the exact same thing as saturated means because you've replaced the 3 means with intercept linear quadratic. It will fit perfectly. Yep. All right, then please finish your homework if you haven't already. You can get started on your formative assessment for next week, and I'll see you Thursday. Let me know if you need anything. Thank you, Zoomers.
Where's Jones?